Today we're continuing our discussion of the properties of rational functions part 2. More specifically, what we're looking at are the horizontal and the oblique asymptotes. We still have examples 3 and 4 to discuss, but I want to point out again that if we have a bottom-heavy function, the degree in the bottom of the fraction is bigger than the degree of the top of the fraction, we will automatically have a horizontal asymptote at y equals 0. If we have the same degree in the top of the fraction and in the bottom of the fraction, our horizontal asymptote is going to be at y equals a over b. And a is coming from the number in front of the highest degree term on the top, and b is coming from the number in front of the highest degree term in the bottom. And then if we have an oblique or a slant asymptote, it's going to be in the format of y equals mx plus b. That's a top-heavy situation where the degree in the top is 1 more than the degree in the bottom. And again, that's a slant asymptote. Will be in the format of y equals mx plus b. And if you watched the video from yesterday, you saw that we had to do synthetic division to come up with our oblique asymptote. But let's flip over here to problem number 3 now, where we left off. And just like yesterday, let's start with figuring out the domain. And ultimately what's going to happen here is that we're going to have to factor both the top and the bottom of this fraction. And I'm not showing my work on factoring this, although it's going to take me 2 steps here. And if we look at the numerator here, we've got x cubed minus 2x squared minus 3x. There's a greatest common factor in that. That's why it takes me 2 steps at least. And if we factor that out, we get x squared minus 2x minus 3. And then we can factor it a little bit more. If you need to, make a note to yourself off to the side that split the middle, because that's the method for factoring. Still working with the numerator, the top of the fraction. And again, I did not show my work for factoring that. In the bottom, x squared minus 4 is x minus 2 becomes x plus 2 when we factor it. And now what we get from there is we can get the domain. And the domain ultimately allows us to determine the vertical asymptote. So our domain is x minus 2 doesn't equal 0. X plus 2 doesn't equal 0. And maybe you don't even need to write those steps. But if we add 2 to both sides, we get x doesn't equal 2. And over here, when we subtract 2 from both sides, we get x doesn't equal negative 2. And I know, I didn't ask for us to figure out the domain on this one. But as we look back here at our function, which I'm going to box in here in red, that's our function in simplified form. We don't have anything to cancel out, which means that our domain and our vertical asymptotes go hand in hand. Our vertical asymptotes are x equals 2 and x equals negative 2, and if you prefer to write x equals plus or minus 2, that's fine. And because we didn't cancel anything out, we do not have any vertical or any removable discontinuity. Let's go ahead and graph our vertical asymptotes right now at x equals 2 and x equals negative 2. There's one, and here's the other. But I'm going to go back and look at I'm going too fast. Let me slow down for a minute. Pause for a second. Let you catch up. we need to determine whether we have a horizontal asymptote or whether we have an oblique asymptote. And that's where that chart comes back into play again. If we look at the top of our function, our degree is the third degree. And our bottom of our fraction, our degree is 2, which means that this is a top-heavy function. If you flip your paper back over and you look at the chart, you're going to see that it's the farthest to the right of your functions. So we just determined that this is a top-heavy function. If we look on our table on the front of our paper, we see that top-heavy means that we're going to have an oblique. It's going to be in the format of the y equals mx plus b. And consequently, because there's an oblique, there is not going to be a horizontal. Now, this one is a little bit different in terms of the synthetic division. But what we're going to do is we're going to take the coefficients on the front here. Sorry. In the top of the fraction. The number in front of the x cubed is 1. The number in front of the x squared is 2. The number in front of the x is 3. And I got my signs in there. It was 1x cubed minus 2x squared minus 3x. But if you think back to synthetic division we cannot use if we divide by x squared. It's limited. It's got to be in the form of x plus or minus a. It has to be a first degree. But the thing is, we factored this. We factored the bottom. We have x minus 2 in the bottom of our fraction. So let's change the minus 2 to a 2 and divide. Bringing down the 1. 2 times 1 is 2. And negative 2 plus 2 is 0. 2 times 0 is 0. And negative 3 plus 0 is negative 3. But that's just part of x squared minus 4. We did the x minus 2. And by the way, we've got x cubed here. When we divide by that first degree, this gives us an x squared. But ultimately, what we're trying to do is we're trying to come up with y equals mx plus b. So we're going to divide again. And the other factor in our denominator, we just did the x minus 2, is x plus 2. And remember, we're going to change the sign on the plus 2 to the minus 2. We're going to carry down this 1. Negative 2 times 1 is negative 2. 0 minus 2 is negative 2. Negative 2 times negative 2 is positive 4. And negative 3 plus 4 is 1. We took x cubed. This became x squared. When we divide it again, this becomes x to the first. And if you think back to our example number 1 from yesterday, what happens is this is 1x minus 2 plus 1 over x squared minus 4, I guess. But we don't need to worry about the remainder. We just need the y equals mx plus b. So I'm going to cross that out. And that's going to give us our oblique asymptote, which is y equals x minus 2. And let's graph that one as well. By the way, our slope is 1 over 1. our y-intercept is -2. Let me try that again. B equals -2. So here's -2. And then a slope, 1 over 1. Up 1 over 1, up 1 over 1, up 1 to the right 1, up 1 to the right 1. You can go down 1 to the left, down 1 to the left. And in general, when I'm drawing, I just leave it like that. I don't even connect it. So now we put in the asymptotes. So let's finish by drawing our picture. So we're going to go to our calculator and we get that picture right there. Just like yesterday, I'd like to suggest that we type in the slant asymptote, because we can, and see, does it make sense to this? Because remember, an asymptote is a line that a graph is approaching, but not quite touching. So if we go back to our y equals here, and we type in, and I'm going to put it in purple here, but the x minus 2. Does that look like it's a reasonable answer? It does. So as we try to draw this, I actually might scan it in here for a moment, just so I have it. And what we have here is we've got something in here. And over here, it looks like we have an intercept there at 0, 0, even though it drops down a little bit here. And then finally over here. And what I didn't look at here, but I should have, 1, 2, 3, there's another x-intercept there. And I did get the x-intercept in here. Looking for some of those key points like the x-intercept and the y-intercept on that graph. Make sure, if you don't know how to use your calculator, that you start asking me. Because it can be a huge help to you on this concept especially. Come on. So one more. And the nice part is that most of this is factored for us already. And as usual, I'm going to start with domain, which means that we do need to factor our denominator. So the numerator is 4 times x plus 1 times x minus 3. And then down here it's x minus 1 times x plus 1. And I hope as you look at this problem, you're thinking, oh, something cancels out, because it does. But before we deal with that cancels out idea, regardless, what's in the denominator is going to determine our domain. So our domain is x minus 1 doesn't equal 0, and x plus 1 doesn't equal 0. And we add 1 to both sides. So we get x doesn't equal 1, and x doesn't equal negative 1. But in terms of vertical asymptotes, it's not going to be both of them, because the x plus 1s cancel out. So since the x plus 1 cancels out, I'm trying to block the right answer here. And what we have is, we have x doesn't equal 1, which means that our vertical asymptote is going to be x equals 1. And the removable discontinuity is coming from the other value, which I forgot to put the not equals on, but I'll put that on now. But our removable discontinuity is going to have an x value of -1, the value that canceled out. So if we determine what the removable discontinuity is, we're going to put that value of -1 back into the part of the function that's remaining. So we still have 4 times the quantity of x minus 3. And down here in the denominator, we have x minus 1. And we're going to put that value of -1 back into our function wherever we see x. So we have 4 times -1 minus 3, all divided by -1 minus 1. Don't put that value back into the original function. We'll get 0 in the denominator. We've got to put it back into the part that's remaining. So this gives us 4 times -4 over -2, which is -16 divided by -2, which is 8. There's our removable discontinuity. And before going too far in this graph, let's go ahead and let's put the removable discontinuity back into the graph along with our vertical asymptote. Those are 2 places that we've got gaps in our graph. X equals 1. And then our other value is -1, 8. -1, 8. 1, 2, 3, 4, 5, 6, 7, 8. It's going to have an open circle. Right there. But maybe the next part is the hardest part. We need to determine whether we have a horizontal or an oblique. And in this particular problem, the nice part is that the numerator is factored. But what we need to know is, what is the degree on the top of this function? Because we need to decide. So if we were to multiply this whole top out, and I hope you don't have to, but if you have to multiply that whole top of the fraction out, what degree would we get? Well, it would be x times x, which would be x squared. That would be the degree on the top. And I know I didn't look at the 4, but we would have to FOIL. We get x squared in the top. And then if you notice in the bottom, we also have x squared. And because we have an x squared in the top and an x squared in the bottom, our situation that we're dealing with is going to be the same degree. And the same degree means that we're going to have a horizontal asymptote, which means that we don't have an oblique. So lastly, then, what we need to determine is, what is our horizontal? It's going to be y equals something. And the thing is, when you look back at that problem, g of x equals 4 times the quantity of x plus 1 times the quantity of x minus 3, we would FOIL x plus 1 times x minus 3. And once we got that FOILed, then we would multiply everything by our 4. So if I can actually get that up here, cancel. Try that again. No. Scoot this down a little bit, maybe. Try it one more time. We actually would have 4x squared when we multiply that out. And because it's the same degree on the top and the bottom, what our horizontal asymptote is going to be is it's going to be the number in front of the highest degree term on top, which is 4, and the number in front of the highest degree term on the bottom, which is 1. So it's y equals 4, if you prefer. If you write 4 over 1, that is fine. It's one more asymptote that we have that we can put back in here. Y equals 4. And then lastly, we'll type it into our calculator. Figure out. Where now? Oh, darn it. Turn this one on. So here's that. Here's that. And again, just scan this in so we can draw the picture relatively easily. And notice, we've got that open circle there, but that's still going to be part of it. And well, it's close enough there. Can't see the y-intercept in this case. But down here, 1, 2, 3, the x-intercept is here. And there's our picture.